Hi guys, my name is Ondřej and today I'll be talking about my project during the summer of HPC. I was based in Dublin in the Irish Centre for High-End Computing, and for the last 8 weeks I've been studying weather regimes during continuous climate simulations. My first task was to set up a climate simulation using the MIT General Circulation Model, which is a large open source project that is in development for almost 2 decades. The application is written mostly in Fortran and employs both MPI and OpenMP. In the second part of my project, I was focusing on post-processing and visualization of the results, for which I was using MATLAB. As the last part of the project, I made some modifications to the MIT GCM package, implementing new features and capabilities. To explain these, I will however have to first get to the basics of climate modeling. All the graphics I am showing in the presentations are some of the results of my project. All general circulation models attempt to solve representations of Newton's equation of motion everywhere in a fluid that is varying continuously in time and space. The continuous fluid, for example the atmosphere, must be discretized in both time and space, and the differential equations replaced with finite difference algebraic approximation. The video in the background shows surface temperature in a simulation of Earth's atmosphere in a so-called Held-Suarez configuration. This configuration represents an idealized atmospheric circulation where land-ocean contrast have been removed, as have all mountains and all other zonally varying boundary conditions and forcing. In other words, the planet is perfectly symmetric. The driving force is the sun's radiation, which sets up a strong north-south temperature gradient. The atmospheric circulation attempts to reduce this by transporting energy polewards. The flow becomes unstable and breaks down into turbulent wave-like patterns. So while the forcing and boundary conditions are zonally symmetric, the final flow is highly asymmetric and fully three-dimensional. Let's change the view of the video in the background. Instead of spherical representation, we will show the surface temperature in the standard latitude-longitude representation. That is the same as looking at a map of the world. The color, however, represents the temperature. The model in the Held-Suarez configuration has relatively few parameters, including, for example, the planet rotation rate, radius, or the gravity. The MIT GCM is designed to set up all parameters at the beginning of the simulation and restricts the parameters from changing during the simulation. As a part of my project, I developed a package for the MIT GCM which allows the parameters to change continuously in a predefined manner, allowing simulations such as the following. Again, we are looking at the latitude-longitude projection of the surface temperature. During the simulation, the rotation period, that is the length of the day, was continuously decreased from 48 to 12 hours. We can see that the number of temperature waves is increasing and their pole-wise reach decreasing, resulting in a reduction of energy transport and consequently in an increase of the temperature gradient. The temperature field is not the only simulation output. Another important characteristic is the wind speed and direction. In this video, we are looking at the zonal component of wind velocity, or otherwise the eastward velocity component. The horizontal axis is the latitude and the vertical is the atmospheric pressure, which is essentially the height. The velocity field is zonally averaged. The high altitude winds in the east direction are an important phenomenon called jets. The Earth has two jets. The one on the northern hemisphere is commonly referred to as the jet stream. With the evolving parameters again, we can see the response of the model in the change of jet's position and also number. With the planet rotating faster, the jets are moving closer to the equator. Many other output characteristics can be studied, such as the other components of the wind velocity. These are the velocity in the north-south direction and the vertical velocity. On this picture we can see cells of upwards and downwards winds, again zonally averaged. For example, the number of these cells corresponds to the Earth's radius. While the changes of these variables, such as the rotation period or radius, are certainly impractical, they should serve to show that the climate we have is only one of many possible. Similarly, increasing greenhouse gases may also shift the Earth's location on the spectrum of climate regimes. That is all by me for now. You can look for more details in my project report and see other output videos here on YouTube. Finally, I would like to thank my supervisors, Enda and Adam, for their help and guidance, and all staff members of iCheck for this wonderful experience.